Remembering the concepts we've talked about so far, including kind of general trigonometry, where we talked about lighthouses, distances, and heights, the GPS constellation and how those circles of equal altitude come together to provide our position, as well as just how like radar navigation works for distances and ranges. If you combine all those concepts, we're going to move forward. In this film, we'll talk a little bit about building a triangle, but a celestial triangle, so that we can use magic tools or publications to help us find our position on Earth. So we've already used the sextant to measure the angle above the horizon for the sun or another celestial body. We've also learned how to compute the geographic position of that. And that is actually going to be one leg of a triangle that we're looking to build on the Earth. So the GP of the object. We already have a built-in point on a triangle as well if we're on a sphere. So we've got the North Pole in my case, or the elevated pole. And the third point of that triangle is what we're going to call the assumed position. Once we create this triangle, this spherical triangle, we can use publications to solve the triangle. We can do that in further steps. But for now, we really want to focus on this assumed position. So a good navigator is going to always know roughly where they are. It's their DR, or dead reckoning position. You're never going to be dropped in the middle of an ocean not knowing roughly where you are. You're somewhere in your passage across an ocean, you'll be able to have an approximate latitude and an approximate longitude. When we build this triangle, though, we're not interested in our dead reckoning position specifically. We're more interested in an assumed position that allows us to do some easy math later on. When we take this assumed position, we're going to complete this triangle and enter some data into HO229 or another tool. It's going to spit back something else. It's going to say, hey, if you were standing at that assumed position, then the sun should be a certain height above the horizon and it should be at a certain bearing. If it is, great. If it's not, we need to do some more work. So my friend here is hungry for dinner, so why don't we feed her and then take the conversation indoors? Just as a reminder, when we talk about objects up in the sky that we observe, they all have a spot on Earth. If you dropped a line directly down, that would be called the geographic position. That is defined as declination and GHA, or the longitude west of Greenwich, or its latitude above or below the equator, depending on your hemisphere. We need to get a little bit more nuanced about some of the terms that are out there. So when we start to build celestial triangles, as we kind of mentioned, we're going to use the pole and some other position. We'll get to that in a little bit. But instead of declination, what the tables actually use is what's known as co-declination. Co-declination is simply 90 minus the declination. This is not something that you need to memorize or use on a routine basis. It's just kind of how the tables are put together. So if you're ever curious about triangles and like why we're using something that's not necessarily part of the triangle, it's because we actually are inferring the co-declination. Another term that would be helpful to kind of understand at this point is if we're out there, on the Earth and we've got our boat and we see an object up in the sky, we're going to be measuring the altitude of that object. That altitude is the distance above the horizon. We measure it with a sextant, we correct it to get it to an HO kind of thing. What we're actually interested though in is the distance from that object to our zenith. The spot directly over our head is called our zenith. The spot directly below us is called our nadir. So this right here is zenith distance. We talked about that when we did the noon sight for latitude, for example. So this idea of like declination and co-declination, or altitude and zenith distance, otherwise known as co-altitude. Don't let it hang you up. It's just some terminology that we'll kind of get through. It's not critical for the actual reduction, but it is helpful to at least have these terms kind of thrown out there. The last term that I'd like to introduce, if this was, say, north on a reasonable portion of the ocean, and this is your boat out there, we said we observed the body above the horizon, that was its altitude. Well, this right here, this direction, and this compass measurement is called azimuth. Azimuth. Another word for that might be bearing. It's always in a 360-degree compass from north. It's the direction from you to the geographic position of that body. That geographic position might be over the edge of the Earth, very, very far away, but the azimuth is the compass bearing to that object. Okay, so we just did a quick review on the geographic position. We introduced a couple of new terms. The second point on our spherical triangle that we're going to use, as alluded to earlier, is the elevated pole. The elevated pole is quite simply the same pole that is in the hemisphere that you are in, not necessarily the GP. So often for simplicity, we draw spherical triangles this way, but if the GP was in the southern hemisphere, the elevated pole would still be in the northern hemisphere in this case. If the GP was in the northern hemisphere and you were in the southern hemisphere, well, we're changing that. The elevated pole is now the south pole, and we build our triangles off that. Likewise, if the GP was in the southern hemisphere and you were in the southern hemisphere, the elevated pole is still the southern one. So although the declination of the body varies from north to south, what defines the elevated pole is where you are. Always remember though that a triangle is kind of like a triangle, whether it's inside out, upside down, or backwards. So however we construct these on the earth, they can all be solved using the tools that we've got coming our way soon. Okay, so we've got 2 points of our triangle. We've talked about the GP and refreshed a little bit on the terminology there. We've talked about the elevated pole and how to define it. Finally, there is the third point of that triangle is somewhere near you. Now, we need to dive into this a little bit more deeply because this is the most critical one and it requires some thought. So let's start out by saying this is your DR position. That's approximately where you were. Dead reckoning accounts for where you have been, your speed, your course, and where you predict you're going to be. So at a certain time of observation, you can plot a DR position, and that should be pretty straightforward. So although we can solve the triangle directly using the DR position and using the law of sines and cosines, we're going to focus on using the tables. In order to use the tables, we need to assume that the people who wrote the tables didn't want them to be super huge, right? And so if they put every possible latitude and longitude, every possible GP, every possible triangle, the tables would be enormous. So instead, like many things in celestial navigation, they put some standard values in there. And these standard values are going to be things that we can use to create what's known as an assumed position. Somewhere near our DR position, not exactly there, but somewhere close, that will create a somewhat standard triangle. There are some rules for this assumed position. So the first rule for the AP is that it needs to be a whole latitude, and it needs to be within 30 minutes of your DR position for best results. So if your DR position was 21 degrees 10 minutes, well, your AP is going to be 21 degrees. If your DR position was 21 degrees 50 minutes, it's going to be 22 degrees for the AP. So round to the nearest latitude within 30 minutes of your DR position. The longitude of the AP is also important, but in a different way. So to create those standard triangles that we can use the tables for, we're going to introduce a term called LHA, or local hour angle. That will allow us to get a standard triangle that we can use tables to solve for. Local hour angle is a relationship between an observer's dead reckoning longitude and the GP of an object. So in the Western Hemisphere, you could define this as your longitude, and that's the Greek symbol for lambda, longitude. You could define this as the Greenwich hour angle. This GHA is an arc from the Greenwich meridian to the meridian of the GP. Whatever's left right there, that's LHA. The local hour angle is the hour angle, or the arc, or the angle between your dead reckoning longitude and the GP's longitude, or GHA. So in the Western Hemisphere, LHA equals GHA minus longitude west. If we were to shift this around to the Eastern Hemisphere, this would be the GHA. From Greenwich to the longitude of the GP, that's GHA. This would be our longitude, right? So a little difference there. GHA is measured always west from Greenwich, whereas our longitude is measured east or west from Greenwich. And that's why this rule is important. But you can see what would be the local hour angle in the Eastern Hemisphere. GHA plus longitude degrees east is going to equal LHA if we're in the Eastern Hemisphere. These two rules of LHA will allow you to calculate a local hour angle so that you can use the tables to solve your spherical triangle later. The key challenge with LHA and longitude, if we go back to our original problem, is we don't want to solve the triangle from our dead reckoning position. We want to choose a standard assumed position so that the triangle can be solved with tables. We already talked about the latitude of the AP. The longitude of the AP plays in with this LHA idea such that you need to pick an assumed longitude, otherwise known as the assumed longitude, which when added or subtracted to the GHA of the body is going to result in a whole number. So we'll end up with whole numbers of latitude and some longitude that is close to our DR position that results in a whole value of LHA. So if we have the whole value of LHA and the whole value of latitude, we can use the tables. So let's say that our DR longitude was like 42 degrees, 20 minutes west. So that's roughly where our DR longitude is. And if the GHA of the sun or whatever body we were using was 95 degrees and 20 minutes, then we need to calculate an LHA. So we said that LHA in the Western Hemisphere was equal to GHA minus longitude west. So 95.20 minus 42.20 is going to equal our LHA of 53 degrees. So that's great. We've got a whole number of LHA. It matches exactly with our dead reckoning longitude, which really never happens. What if instead our DR longitude was 42.30, right? And so now this math is going to change. You know, our LHA is gone here. If our DR longitude was 42.30 and the GHA was 95.20, well, what we need to do is we need to assume a DR longitude or an assumed longitude that when added or subtracted to the GHA results in a whole number. So in this case, again, LHA is GHA minus longitude west. GHA is known, 95 degrees 20 minus what is going to result in a whole number? Well, 42.20, just like before. So our DR longitude needs to be close to this, but it doesn't need to be the exact thing. So we just write down a note that our assumed longitude was 42.20, and we keep that for later in like step 5 when we do our process. So as long as we assume a DR longitude or an assumed longitude relatively close to our actual DR, and that the math for LHA works out to be a whole value, we are good to go. So this requires some practice. I would put some effort into that, and we'll move on from there. Okay, here's where the rubber meets the road for step 3 of the process. We need to create 3 values so that we can build a spherical triangle. We need to know the GP, the AP, and the elevated pole precisely so we can build that triangle and then go into the tables to solve it in step 4. In order to go into the tables, we really need 3 key pieces of information. We need declination in whole value of the body. We need latitude in whole body for the assumed position, and we need LHA in whole value for this relationship between the longitude and the GHA of the body. We need this angle. So thinking back to triangles again, if we know 2 sides and an angle or 2 angles and a side, we can solve the triangle. The tables will do it for us. So here's an example. If this was our situation, the GP of the body was 2315 north, 144.46 west. That's the GP. And our DR latitude and longitude was 5515, 3230. What values would we choose to go into the tables with to kind of solve this triangle later? Well, declination, number 1. It needs to be a whole value and it's truncated. So you don't round it, you just choose the lower limit, the whole value of declination. So it's 23 degrees north in this case. If this declination was 2345, it would still be 23. We account for that part of the triangle later. All right, latitude, the next easiest one. Our DR latitude was 55.15, so the latitude we choose is going to be 55 degrees north. We kind of round to the nearest 30 minutes. If this latitude was 55.45, we would choose 56 different than declination. So just remember that, the rules of how we do this. And then finally, LHA, we need a whole value of LHA. We're in the Western Hemisphere, so LHA equals GHA minus longitude west. The GHA is 144.46. What longitude do we assume so that this math comes out to be a whole number? Well, our DR longitude is 32 degrees 30. It's not going to work. But as long as we stay within 30 minutes of time, of arc rather, we can change this to 32.46. And now our LHA is going to subtract in a whole number to be 112 degrees. So our LHA is 112 and our assumed longitude is this. We do need to retain that information for later. It changes our plotting position for step 5. So when given a triangle and 3 arguments in whole values, can you select the correct ones to enter the tables and solve the problem efficiently? So practice these problems and then you'll be pretty good with step 3. There's a few other things we can do with this information that I've included in this part of the course. We'll focus on that next, but this is the core skill, the key skill for step 3 of the celestial process. When you think about the Earth, if you were to divide it exactly in half with a lightsaber, if you were to chop it in half kind of thing, such that that lightsaber went through the center of the Earth, it would impact kind of in a plane, it's pretty hard to draw, but it would impact in a plane and it would kind of slice that Earth in half. If you then looked at that Earth and kind of traced that arc over the surface of the Earth, it's going to define the shortest distance between any 2 points on the surface of a sphere. This is what's known as a great circle. So a great circle. And if you've ever taken a long distance flight, and you're leaving from location A and to go into location B, and you look at the little map in the seat in front of you, rather than take a straight line, you often take a curved line. That's because this represents the great circle on a spherical Earth represented in a flat plane. So there are certain charts that will allow you to kind of view these great circles as straight lines. They're called mnemonic charts. But for the purposes of this course, I wanted to illustrate that a great circle is what's known as an hour circle. An hour circle for celestial navigation is something that's a great circle on a sphere that passes through not only the Earth, but the celestial poles in a celestial body. So when we represent it on Earth, we kind of refer to things as the Greenwich hour angle of something. That's the GHA. But it actually can be kind of sliced through the Earth. It's a great circle representing kind of the angular distance from a longitude on Earth to the spot directly beneath a celestial longitude up in the sky. Likewise, there are a couple of other hour circles that are important, and we've really already talked about them. There is the Greenwich hour circle. Oops, I always spell that wrong. The Greenwich hour circle. There is the local hour circle, which kind of defines your longitude. There is also the Aries hour circle, which is helpful to determine what's known as SHA, or sidereal hour angle. And so that's kind of what I want to focus on in this little astronomy video, is Aries itself. Aries is a constellation up in the sky, and if you were sitting on Earth right over Greenwich, England, I'll try and spell it correctly this time, Greenwich, England, on the vernal equinox, kind of the spring equinox, at a certain time, that's when the first point of Aries passes the longitude of Greenwich. So if you're kind of looking south here, in that direction, you're looking past the city, the sky is rotating from left to right from your perspective. The first point of Aries passes the Greenwich meridian on the vernal equinox. Now, it's important to note that occurred when this thing was named. It doesn't happen every year. It's not like a defined situation. But Aries itself is a constellation. The first point of Aries is kind of what crosses Greenwich on the vernal equinox when it was named. And then it allows you to measure the sidereal hour angle from the first point of Aries to a star to kind of determine the GHA of that star. So we've talked a little bit about this already when we were kind of referring to stars and kind of turning them from HS to HO. But at this point, a little bit of astronomy is kind of a little bit helpful. So looking at it from the Earth perspective with kind of our standard diagram now, if this is Greenwich and this is the GP of Aries, so we would represent that as the GHA of the first point of Aries. And then stars are always listed west of Aries. So if there was a star with its GP over here, this would be the SHA, and this whole thing would be the GHA of the star. Likewise, if there was a star like way over here, this is the SHA, and then this is the GHA of that star. So the formula, if you're a formula person, the first point of Aries plus the SHA equals the GHA of the star. Okay, in the previous couple of videos, we've talked a little bit about LHA and Aries, but not together. So with these two skills, you can unlock a couple of new challenges for celestial navigation. The one we'll talk about in this video is known as the Star Finder, or the Rude Star Finder, sometimes named after a person, or the 2102D tool. The key for the Rude Star Finder is the LHA of Aries. So we know what LHA is. We just refreshed ourselves on what Aries is. How do we calculate the LHA of Aries? Well, it's relatively straightforward. Let's say it was 17 March, and you observed like an unknown star out on the horizon. It had an azimuth of 320 degrees true, and it had a height of height observed, or an altitude is another way to say that, of 50 degrees. What star did we observe? Well, we need the Rude Star Finder, the 2102D, to do that. In order to use that, we need to get the LHA of Aries. So some more information. Let's say our DR position was 25 degrees north, and our DR longitude was like 66 degrees 48 west. The next step would be to kind of get the GHA of Aries. So in this problem, we're going to say it's given to us because we want to focus on kind of other learning objectives. Let's say the GHA of Aries was 156, 53.7. What star did we observe? Well, to use the Rude Star Finder, you're going to need to use the white plates, which are set to the north or south hemisphere. And you're going to need to use the clear plates, which are set to certain latitudes. So in this case, we're going to use the clear plate for 25 and the backing plate for north. So we can set up the Rude Star Finder that way. The only other bit of information you really need is the LHA of Aries. And so the LHA of Aries is pretty straightforward to calculate. You just take the GHA of Aries, which we said was 156, 53.7. And our DR longitude is 66 degrees 48.0. The LHA of Aries is just going to be this subtracting this. So 156, 53.7 minus 66.48, because we're in the Western Hemisphere. If we were in the Eastern Hemisphere, we would be adding those two together. So the LHA of Aries, if we do this math, comes out to be 90 degrees 05.7. You're like, wait a minute, that's not a whole value of LHA, right? Well, we don't need a whole value of LHA for this task. We only need the whole value of LHA to use the site reduction tables in step 4 and 5 of our celestial reduction process. To use the Rude Star Finder, we just need an LHA of Aries. Now, truthfully, you can just kind of round this value to 90 and it's going to be totally okay. Once you spin the Star Finder to an LHA of Aries of 90 degrees, you can then search the Star Finder for an altitude of 50 and an azimuth of 320, and you're going to see that Murphak is the closest star in this case. So the Star Finder is a great tool for you to practice with and identify unknown objects, or pre-identify objects that might be helpful for you to sight if you're in an unfamiliar part of the ocean or the unfamiliar part of the sky. We live at a time in which the star Polaris sits generally above the North Pole of the Earth. Despite its, orbital tilt and all that kind of irregularities, Polaris is relatively close to directly overhead from the North Pole. Otherwise, its GP is 90 degrees north. Now, it's not exactly 90. It wanders just a little bit. So if we were to kind of portray it this way, straight up from the North Pole, the star does have a very slight orbit around that pole. And for that reason, navigators can use Polaris to estimate latitude very easily with a couple of minor corrections for this little stuff that's going on right there. So if the star were directly overhead, if you were standing at the North Pole, you would be at its GP, the HO would be 90, and your latitude would also equal 90. If you moved, say, a little bit away from it, now you've got an angle that you can measure. And let's say you measured 89 degrees. So your HO is 89. Well, with a couple of corrections, that's going to be your latitude. So that's the benefit of Polaris as you kind of move further and further away in the northern hemisphere. The HO is pretty much the latitude. We do need to account for that tiny little orbit up there. And so in the Nautical Almanac, there is a Polaris table. And you need a few things to use this table. You need the LHA of Aries, which we've talked about in a few recent episodes. You need your DR latitude to the nearest 10 degrees, roughly. And you need the month of the year. With these three bits of information, you can use the Polaris tables to help calculate the latitude that you're at. The formula is going to be your latitude equals the height observed, which is already corrected for atmospheric refraction and dip and all that, minus 1 degree, plus A0, A1, and A2. These correspond to these three things that you need. All right, so let's take a look at kind of an example problem using the star Polaris to get our latitude. So let's say we found ourselves with an HO of 5230 for the star Polaris. It was April. We were approximately 50 degrees north latitude. That's very approximate. And we had previously calculated the LHA of Aries to be 115 degrees. There's usually more to this process, but to illustrate the learning objectives for this lesson, we want to focus on that. So you'll open to the Polaris tables, and we'll kind of just use these little corrections to guide our process here. So the first one is going to be for the LHA of Aries. And as you look at the Polaris tables up here, you can see LHA of Aries, it's listed in 10-degree increments with the additional 1-degree increments over here. So if our LHA of Aries was 115, the correction we're going to make is 52.1. 52.1. So let's just note that. So that's going to be 52.1. If the DR latitude was 50 degrees, you stay in this same column, and the correction we're going to make is 0.6. So once you're in the LHA column, you stay there. And then for the month of April, in the same way, 0.9. The good thing about the Polaris tables too is it does give you the formula down at the bottom so that you can remember it's minus 1 degree plus the three corrections there. So if these corrections are going to be 52.1, 0.6, and 0.9, we can refer to the latitude formula down here, which says it's the apparent altitude minus 1 degree plus these three corrections right here. So we do need to add all three of these corrections and minus 1 degree from it. So the process would be, here's our HO, minus 1 degree plus 52.1 minutes plus 0.6 minutes and plus 0.9 minutes. Through the magic of a calculator, we can take 52 minus 1 degree, add up all this stuff, and then it's going to end up being an answer of 52 degrees, 23.6 minutes for our latitude.